Figure 4 shows how the pH changes as 0.1 mole per decimetre cubed sodium hydroxide solution is added to 25 centimetres cubed of 0.08 mole per decimetre cubed propanoic acid. And we're adding sodium hydroxide a little bit at a time and measuring the pH. And our concentration of sodium hydroxide is 0.1 mole per decimetre cubed. Propanoic acid is a weak acid. State the meaning of weak. Weak means partially dissociated or partially ionized. So it's only partially dissociated into its ions. Suggest why a student doing an experiment to produce the curve in figure 4 would add the sodium hydroxide dropwise here around the equivalence point. So why would we do it dropwise there? And that's because there is a large pH change at equivalence so NaOH is added dropwise as pH is changing very rapidly, and we want to get enough data about how it's changing. Give an expression for Ka. So Ka is the acid dissociation constant, which is when the ion partially dissociates into its ions, when the acid, partially dissociates into its ions. So Ka, products, propanoate ion, proton, H+, over propanoic acid in square brackets to represent concentration. Use this expression to show that pH equals pKa when half the propanoic acid has reacted. So we started off with all propanoic acid, and over time our propanoic acid is being converted. So we've got propanoic acid and it's being converted into propanoate ions over time. When half of it has reacted, we're at this midpoint. So when half the propanoic acid has reacted, half of it's gone. So if you're struggling to see it, let's imagine we had 10 at the beginning and none. When half of this has gone, 5, there'll be 5 of this because half of it has gone. So half, we've made the same amounts. It's a 1-to-1 ratio as we've used up. So the amounts of HA and A- are equal. And if those two things are equal in that Ka expression, then Ka just equals H+. And if Ka equals H+, then pKa minus log of Ka equals pH minus log of H+. Use the pH from figure 4 when half the propanoic acid has reacted to calculate the Ka. So we need to go back to figure 4 and let's have a look. So the equivalence when it's all reacted is here at 20. Okay, so we're looking at the pH. This is when it's all reacted. So we want to go to half of that, so to 10, when half of it has reacted. And we want to go up here to the line and go across from there. Just going to move that down ever so slightly because there we go. And that would be our pH. So that looks like to me, if this big square is worth 2 pH units. Each little square is worth 0.4. So this is like 4.6-ish. It's halfway between 4.4 and 4.8. So pH equals 4.4. The exam board allowed, I said 4.6 is what I said, and it allowed anything between 4.4 and 4.7. Okay, so if the pH in my answer is 4.6, then pKa equals 4.6. So Ka equals 10 to the minus of my answer. So I'm going to, on my calculator, do 10 to the minus 4.6. Again, using whichever pH value you've chosen, 2.51 times 10 to the minus 5. When sodium hydroxide solution is added to aqueous propanoic acid, the solution formed acts as a buffer when between 5 and 15 centimetres cubed have been added. Explain why the pH stays approximately constant during this part of the experiment. So this is, if we go all the way back to the graph, this is why it's sort of almost flat between 5 and 15. It's not changing very much. So the OH minus ions that are added, so remembering that your buffer is a mixture of HA, the weak acid propanoic acid, and A minus, CH3, the propanoate ions. Which one would OH minus react with? They're going to react with HA, the propanoic acid. So the equilibrium, and you need to specify what equilibrium you're talking about. I'm going to do the dissociation equilibrium. This is this equilibrium, so I'm going to write it out as well. So if we're reacting with the propanoic acid, we're going to make more propanoate. So you could say reacts with propanoic acid, or you could say reacts with the H+. Equilibrium for dissociation shifts right to replace the H+. And the ratio of the concentration of CH3, CH2, COOH to CH3, CH2, COO minus remains constant. So on this top part, you could have said either propanoic acid or H+. They're reacting to make more salt and replace any H+ that had been removed. Methyl orange and universal indicator are not suitable indicators for this titration. Why not? Well, methyl orange is an indicator that it is suitable, has a pH range that is fairly low down on the pH curve, between about 4 and 6. So it kind of changes colour here. So its pH range does not fall within the vertical region of rapid pH change. So pH range of the indicator does not match the equivalence point, or it doesn't match the region of rapid pH change, doesn't match the vertical part of the curve. The The problem with universal indicator is it has a range of colours, not one distinct colour change, over many pHs. Would not give a distinct colour change at equivalence.